Hello again. This is going to be Chapter 2 of Physics 1, or Physics 201, if you're with Judson. We're going to be discussing velocity, displacement, acceleration, all of those kinds of things. These are going to be vector quantities, and you'll soon learn how to represent those. So the first thing that we're going to talk about is displacement and how that plays into velocity. So when an object moves along a straight line, we're going to describe its position with respect to an origin O by means of a coordinate, such as x. So if the object starts at position x1 at time 1 and arrives at position x2 at time 2, the object's displacement is a vector quantity whose x component is going to be represented with delta x, or change in x, x2 minus x1. The displacement doesn't depend on how it got there, just the fact that it got there. The rate of change of position with respect to time is given by the average velocity. It's a vector quantity whose x component is going to be the change in x over the change in time, represented here. So if you take it and draw it out on a graph, you've got time in this direction, you've got x in this direction. You're going to see the displacement here drawn in blue, and you've got a car moving in the x direction, so it starts here and ends there. And it starts at x1 at time t, it ends at x2 at time t2. So on that graph, the v average is going to be represented with this. Is going to be the slope of the line connecting this point to that point. As the average velocity is calculated for progressively small intervals of the change in time, the average velocity approaches the instantaneous velocity, which, if you've had calculus, is going to be the limit as delta t approaches 0 of delta x divided by delta t. That's going to represent, this quantity is going to represent the velocity at any particular time, and it's going to represent the tangent line as the blue line goes from here to here. That plays into acceleration. So when the velocity of an object changes with time, we say that the object has acceleration. In other words, if your velocity is increasing or your velocity is decreasing, you're changing the velocity. That phenomenon is going to be referred to as acceleration. So just as the velocity describes the rate of change of position with time, acceleration is going to do what I just described, that change in velocity with time. If we're going to look at the average acceleration in the x direction, it's going to be the velocity at some time 2 minus the velocity where it started, and then divided by the time difference between the two. So the change in v over the change in t. The average acceleration, again, is going to be the slope of this line. And as with velocity, when the average acceleration is calculated for smaller and smaller intervals of time delta t, then it's going to approach the instantaneous acceleration, and that's going to be represented by a tangent line at some point along this black line. That's, again, if you've had calculus. So, motion with constant acceleration. When an object moves with constant acceleration in a straight line, you're going to have three primary equations that are going to describe the motion. In these equations, x naught and v naught in x are respectively the position and velocity at the time t of 0, and x and vx are the position and velocity at a later time t. Those equations are listed here. The velocity at x is going to be the same as the starting velocity plus the acceleration in the x direction times t. If you want to consider the position here, the final position is going to be the same as the starting position plus the velocity, the starting velocity in the x direction times t plus 1/2 at squared. You can also relate the velocity in the x direction squared, which is equal to the initial velocity in the x direction squared plus 2a times x minus x naught. To go through those derivations, if we go to section 2.4, we can see these equations written here. And if you change this around, if you say this is equal to 0, then you can easily see how this equation can be changed to look like this. We've got some problems here that you can work through. For the average velocity in the x direction, it's going to be the average of the starting and the ending divided by 2. And once you also know that this velocity, the velocity at any given time t, if you substitute that in for Vx, then you can rearrange the equation, and then you can have how the velocity at a particular time at x is going to be the same as your starting velocity plus 1/2 at squared. And then again, you can come up with this third equation here through some continuous torturing of those equations. Those three kinematic equations are what you're going to need going forward in order to be able to solve these problems. And again, I will let you go through and work through these problems yourselves, and those are very good exercises. Proportional reasoning. Many problems have two variables that are related in a simple way. They might be related linearly, y is equal to x. You could have a quadratic form in which you have y is equal to x squared, where now you have an exponent of 2. They could be inversely related, where y is equal to 1 over x, or they could be inverse square related, y is equal to 1 over x squared. It depends on the type of variable. It depends on what two variables you're putting together, but these are the common relationships that you're going to see. If you graph them, these are what they're going to look like. For section 2.6, a freely falling object is an object that moves under the influence of a constant gravitational force. The term free fall includes objects that are initially at rest, as well as objects that have an initial upward or downward velocity. The basic is if you take these equations, you write them in the y direction as opposed to the x direction, and then you introduce an acceleration constant called g, your gravitational acceleration. It's approximately going to be 9.8 meters per second squared. So these equations are changed to this, and A is going to be changed to G. Same concepts, just a different direction. You're looking up and down as opposed to linear, horizontally. So relative velocity along a straight line. When an object P moves relative to an object B, let's get this in. Okay, so you've got an object P, you've got an object B, and B moves relative to a second reference frame A, we can denote the velocity of P relative to B, and they do a velocity with P line B. The velocity of P relative to A is going to be the velocity of P at line A, and the velocity of B relative to A is V with B line A. Putting all of this together, you're going to have the velocity of P with respect to A is going to be the velocity of P with respect to B plus the velocity of B with respect to A. In other words, how this moves relative to this is going to be the same as how this moves relative to that, and then how this is moving relative to this. By adding all of these vectors together, you can kind of see the relationships between how all these work. You've got the velocity of p relative to a is equal to the velocity of p relative to b plus the velocity of b relative to a. The magnitudes are all the same. Depending on how you add them up is how you can get the vectors running in the same direction.